This is SpaceTime, Series 20, Episode 35. Coming up on SpaceTime, scientists solve the mystery of the Milky Way's mysterious gamma-ray glow, discovery of a gravitationally lensed supernova, and Cassini finds a big empty close to Saturn. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A mysterious gamma-ray glow coming from the centre of the Milky Way galaxy is most likely being caused by a sea of pulsars. The findings, reported in the Astrophysical Journal, cast doubt on previous hypotheses that the glow might be evidence of dark matter, a mysterious invisible substance which accounts for 85% of all the matter in the universe, but which so far has evaded detection. Pulsars are rapidly rotating neutron stars, the incredibly dense, highly magnetic spinning cores of collapsed stars that were up to 30 times more massive than the Sun. The study's lead author, Mattia DeMoro from Stanford University and the United States Department of Energy's Stanford Linear National Accelerator Laboratory, says the findings show dark matter isn't needed to understand the gamma-ray emissions from the galactic center. Instead, the authors have identified a population of pulsars in the region around the galactic core, which may shed new light on the formation history of the Milky Way galaxy. DeMoro and colleagues use NASA's Fermi Gamma-Ray Space Telescope to examine the gamma-ray glow in detail. Dark matter is one of the biggest mysteries of modern physics. Astronomers know dark matter exists because they can see its gravitational impact on normal matter, how it bends light from distant galaxies and affects how galaxies rotate. The trouble is, they have absolutely no idea what dark matter is actually made of. Most scientists believe it's composed of yet-to-be-discovered particles that almost never interact with regular matter other than through gravity, making it very hard to detect. One way scientific instruments might catch a glimpse of dark matter particles is when those particles either decay or collide and destroy each other, and some hypotheses predict that these processes could produce gamma rays. And so researchers have been using Fermi to search for this radiation in regions of the universe which are supposed to be rich in dark matter, such as the centre of our galaxy. Previous studies have indeed shown that there are far more gamma rays coming from the galactic centre than expected, and that's fueled several scientific papers suggesting that the signals may provide hints of the long sought-after dark matter particles. The problem is gamma rays can be produced by a number of other cosmic processes, and these firstly need to be ruled out before any conclusions about dark matter can be drawn. The problem is even more challenging because the galactic centre is extremely complex. You see, astronomers aren't entirely sure exactly what's happening in this region, which surrounds the galaxy's central supermassive black hole, Sagittarius A star. Most of the Milky Way's gamma rays originate in gas between the stars that's lit up by cosmic rays, charged particles commonly produced by supernova explosions. And this creates a diffuse gamma-ray glow which extends throughout the galaxy. Gamma rays can also be produced as byproducts of supernovae such as pulsars, collapsed stars that emit beams of gamma rays like cosmic lighthouses. Gamma rays can also be produced by more exotic objects, appearing simply as points of light in the distant sky. Two recent studies by teams in the United States and the Netherlands have shown that the gamma-ray excess in the galactic centre is speckled, not smooth as would be expected from a hypothetical dark matter signal. The results suggest that the speckles may be due to point sources, but Fermi couldn't isolate these as individual sources because of the high density of gamma rays causing the diffuse glow, which appears brightest in the galactic centre. So the new study takes these earlier analyses to the next level, demonstrating that the speckled gamma-ray signal is consistent with pulsars. DeMoro says that considering that about 70% of all point sources in the Milky Way are pulsars, they are the most likely candidates. And because pulsars have very distinct spectra in terms of how they emit gamma-ray energy, the authors were able to use the shape of these spectra to model the glow of the galactic centre correctly, matching a population of about 1,000 pulsars. They were able to show there was no need to introduce any sort of dark matter particle in order to achieve their results. The team are now planning a series of follow-up studies using radio telescopes. That will help them determine whether the identified sources are emitting their energy as a series of brief light pulses, the trademark that gives pulsars their name. Discoveries in the halo of stars around the centre of the galaxy, the oldest part of the Milky Way, also reveal details about the evolution of our galactic home, in the same way as ancient remains teach archaeologists about human history. You see, isolated pulsars have a lifetime typically of around 10 million years, and that's much shorter than the age of the oldest stars in the galactic centre. The fact that astronomers can still see gamma rays from the identified pulsar population today suggests that the pulsars are in binary systems with companion stars from which they're leaching energy, and thereby significantly extending their lives. The new results add to other data which is already challenging the idea that gamma-ray excess is a dark matter signal. You see, if the signals were due to dark matter, astronomers would expect to see similar gamma-ray signals emitting from the centres of other galaxies as well. And those signals would be especially clear from dwarf galaxies orbiting the Milky Way. That's because dwarf galaxies have very few stars, they typically don't have pulsars, and they're usually held together by lots and lots of dark matter. The problem is, scientists haven't detected any significant gamma-ray emissions coming from dwarf galaxies. The authors believe the recent discovery of a gamma-ray glow coming from the centre of the Andromeda galaxy M31, the biggest nearby galaxy to the Milky Way, could also be caused by a large population of pulsars rather than dark matter. However, the last word on this story may not yet have been written. You see, although the authors studied a large region around the galactic centre, the extremely high density of sources in the innermost region of the galactic core makes it extremely difficult to see individual emission sources and thereby rule out a smooth dark matter-like gamma-ray distribution. And that leaves at least some wiggle room for dark matter signals to hide. This is SpaceTime. I'm Stuart Gary. Astronomers have discovered their first gravitationally lensed thermonuclear supernova. The new observations, reported in the journal Science and on the pre-press physics website archive.org, could provide new ways of studying the accelerating expansion of the universe due to a mysterious force called dark energy, as well as gravity and the distribution of dark matter across the cosmos. As mentioned earlier, a supernova is the catastrophic explosive destruction of a star. These spectacular blasts are bright enough to briefly outshine an entire galaxy. A thermonuclear or Type 1a supernova occurs when a Sun-like star in a binary system with another star gravitationally draws a lot of material off the companion star. Eventually, the progenitor supernova star reaches what's known as the Chandrasekhar limit, which equates to a mass of about 1.4 times that of the Sun. Now, once a Sun-like star reaches this specific limit, its core can no longer support the tremendous amount of mass pressing down on it, and the star explodes catastrophically in a thermonuclear or Type 1a supernova. Because all Type 1a supernovae occur at around the same mass, the stars always explode with about the same amount of luminosity. And so astronomers can use them as standard candle cosmic distance markers, allowing them to determine cosmic distances across the universe using a formula called the inverse square law. The inverse square law eloquently describes the intensity of light at different distances from a light source. For example, although all the streetlights on a road will be of the same strength, those further away will look dimmer compared to the ones nearby, and the further away the streetlight is, the dimmer it will appear. That's the inverse square law in action. The other part of this story concerns something called gravitational lensing. First predicted by Albert Einstein in his theory of general relativity, gravitational lensing occurs because mass bends the fabric of space-time, so that light from a background object, such as a supernova, will be bent or lensed by the mass of a foreground object, such as a galaxy. The thing is, imaging a gravitationally lensed thermonuclear supernova has proven extremely difficult until now. But that all changed on September the 5th, 2016, when astronomers detected a thermonuclear supernova candidate using two Caltech-led international scientific collaborations, the IPTF, or Intermediate Palomar Transient Factory, and GROWTH, the global relay of observatories watching transients happen. The IPTF takes advantage of the Palomar Observatory and its unique capabilities to scan the skies and discover fast-changing cosmic events in near real time. Things like fast radio bursts, gamma-ray bursts, and in this case, supernovae. Meanwhile, GROWTH manages a global network of researchers and telescopes to quickly undertake detailed follow-up observations of these transient events. At first glance, the newly discovered supernova candidate, which was named IPTF-16GEU, looked like it was about 1 billion light-years away. And like most supernovae that are discovered relatively early on, this event got brighter with time. Shortly after it reached peak brightness, astronomers decided to take a closer look at the supernova candidate and obtain a spectrum. That is a detailed light study which will allow them to better understand its composition and distance. The results confirmed that it was indeed a Type 1a supernova. But they also showed that, surprisingly, it was located some 4 billion light-years away. That's 4 times more distant than originally thought. The authors then turned to the giant Keck telescope on Mauna Kea in Hawaii and the European Southern Observatory's VLT, or Very Large Telescopes, in Chile. A second spectrum taken with the OSIRIS instrument on Keck confirmed without a doubt that this supernova was indeed 4 billion light-years away. It also revealed the supernova's host galaxy, and surprisingly, another galaxy located about 2 billion light-years away that was acting as a gravitational lens, which amplified the brightness of the supernova, causing it to appear in 4 different places in the sky. The study's lead author, Professor Ariel Gubar from Stockholm University, describes resolving the supernova for the first time and then seeing its strongly lensed multiple images as a major breakthrough. This discovery will allow astronomers to measure the light-focusing power of gravity more accurately than ever before. It also allows them to probe physical scales that previously seemed to be out of reach. Within 2 months of detection, the team had also turned the Hubble Space Telescope on the supernova. Astronomers were then able to very accurately measure how much time it takes for the light from each of the multiple images of the supernova to reach us here on Earth. And that difference in time of arrival can then be used to estimate with a really high degree of precision the expansion rate of the universe, a figure known as the Hubble constant. Currently, the different methods used to measure the Hubble constant all produce slightly different results. But even these small changes can result in significantly different scenarios for the predicted evolution and expansion of the universe. As well as all that, using the data from Keck and Hubble, the authors were able to discover that the lensing galaxy needed to have a great deal of substructure in order to account for the total lens magnification, as well as the observed differences of the 4 separate supernova images. And that means the findings could introduce new questions about the way matter clumps in the universe, challenging science's understanding of gravitational lensing on small scales. To find out more, Andrew Dunkley is speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
These are very special images of a supernova. So let's just recap. A supernova is a star that explodes at the end of its life. There are a number of different mechanisms by which stars can explode. They've got to be massive ones, much, much bigger than the sun, 10, 20 times the mass of the sun. Our sun will never exhibit such bad behavior because it will gently come to an end in 3 or 4 billion years' time. Put that in your diary while we're talking about it. But a supernova is an explosion of terrifyingly large proportions, and they're very well observed. And one of the things we know about them, at least supernovae of a particular type, is that you can use them as standard candles. They all go off with the same amount of brightness.
Is that right?
These are so-called supernova of type 1a. And that means that they're useful. So to have something whose brightness you know, and then you can measure that from Earth, that gives you an idea of how far away it is. And indeed, it was by looking at these supernovae back in 1998 that the discovery was made that our universe is expanding ever faster, that the expansion of the universe isn't constant.
Oh, with all these things blowing up inside the universe.
That's right. It could only be expanding fast. Yeah. But the trick with this one, and the reason why this particular set of observations has hit the headlines, is that this combines exactly what we've just been talking about, measuring the brightness of a distant supernova, but it combines it with a phenomenon called gravitational lensing. And that is basically the distortion of space caused by massive objects. And the massive object in this case is a galaxy that sits between ourselves and this distant supernova. So this galaxy is kind of in between us and the object that's exploded. And the galaxy itself has mass. It distorts the space around it. It's a very well understood phenomenon. And what you get, instead of just one image of the supernova, we've got 4 of them arranged in a beautiful, almost a square, around the image of the galaxy. So why does that help? Well, it's almost a bit of magic that takes place here, because as the 4 distorted images of the supernova are formed by the gravitational lens, what it does is gives the light path to each image a slightly different timing. So some of the explosion, the light of the explosion of the supernova, takes a slightly longer dogleg path to get to us than other parts of it. And so what you get,
like the air over an aeroplane wing, for example.
Exactly, yes, it's very similar to that. The wing distorts the airflow, and the air over the top takes a longer path, and because of that you get lift. It's an analogous situation. What you've got is the light taking a longer path around one side of this lensing galaxy, as it's called, compared with the other side. Now, unlike airflow over an aeroplane wing, the speed of the light can't change. So the speed of the light is the same at all times. So what that means is that the pulse of light from the supernova arrives slightly later for the image that has gone the long way round, if I can put it that way. And so you get this time delay between the four different images that we're seeing. It's a complex story, but what it means is that you can use that time delay actually to learn things about the expansion of the universe. It sort of tells you how fast space is expanding, because you can plug into all kinds of complex mathematical equations the time delay that you get, and it's actually a very powerful tool. So that is why this Swedish team of astronomers is so excited about this, and we may find coming out of it some kind of new high precision measures of, well, the age of the universe, how much its expansion is accelerating by, and things of that sort. This is work that is in progress, but I think will tell us a lot more about the universe than we know already.
Does this particular supernova have a name that they've been studying? You got it? Look, I have to know.
It does. It's called IPTF 16GEU. Yeah, there you go.
Well, it's good that we can actually learn something from these things. I mean, supernova are just spectacular when they're seen, and they have been seen with the naked eye.
The only one in our lifetimes was in 1987, and that was visible in the Large Magellanic Cloud. The last naked eye supernova before that was in 1604. So they're pretty rare, yeah.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And you're listening to Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important, or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. In the last episode of Space Time, we told you about Cassini flying between the rings of Saturn and the planet itself. We can now update that story because, thanks to Cassini, NASA's scientists can now say the region between Saturn and its rings is relatively dust-free. Although, to be honest, the discovery made during Cassini's first plunge inside the rings has come as somewhat of a surprise. Cassini project manager Earl Mays from NASA's Jet Propulsion Laboratory in Pasadena, California, says the region between the rings and Saturn is apparently a big empty. Models of the ring particle environment in the 2,400 kilometre wide gap between Saturn's swirling cloud tops and the inner edge of its spectacular ring system suggested a relatively particle-free environment for Cassini's passage. However, because no spacecraft had ever travelled through the gap before, mission managers decided to position Cassini's 4-metre wide high-gain antenna dish in front of the spacecraft as a shield, just in case. Cassini's radio and plasma wave science instrument had detected hits from hundreds upon hundreds of ring particles per second when the spacecraft crossed the ring plane just outside of Saturn's main rings. But strangely, it only detected a few pings during the inner ring crossing. When the radio and plasma wave science data was converted into an audio format, dust particles hitting the instrument's antennas sound like pops and cracks, covering up the usual whistles and squeaks of waves in the charged particle environment the instrument's designed to detect. And so scientists expected to hear lots of pops and cracks on crossing the ring plane inside the gap, but instead it was the whistles and squeaks which came through surprisingly clearly. The team's analysis suggests Cassini only encountered a few particles as it crossed the gap, and none larger than those in smoke. In other words, about a micron in diameter. So scientists will now work on the mystery of why the dust levels are so much lower than expected. Of course, Cassini's now going through what mission planners are calling its grand finale. During this final chapter in its journey, Cassini loops Saturn approximately once a week, diving between the rings and the planet. The flight path is designed to position Cassini for what will be a final suicide death plunge on September the 15th, bringing to an end the 20-year mission. The decision to end the mission in a fiery grand finale is based on the need to ensure the probe doesn't contaminate any of Saturn's moons with microorganisms from Earth that may have stowed away aboard the spacecraft. Launched back in 1997 on a Titan Centaur rocket from the Cape Canaveral Air Force Base in Florida, Cassini arrived at the Saturnian system 7 years later in 2004. Its mission revealed the ringed world and its many moons to be far more mysterious and spectacular than scientists could ever have imagined. This is Space Time. I'm Stuart Gary. SpaceX has successfully launched its first top-secret spy satellite for America's National Reconnaissance Office. It was a case of second time lucky for the classified payload after a faulty first-stage liquid oxygen temperature sensor detected an anomaly the previous day, resulting in the launch being scrubbed. The NROL-76 payload was blasted into orbit aboard a Falcon 9 rocket from Pad 39A at the Kennedy Space Center at the Cape Canaveral Air Force Base in Florida.
Go for launch. Stage 2, pressing for flight.
T-minus 20.
Stage 1, pressing for flight.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff at Falcon 9.
Copy, loco.
First stage shutdown and main engine cutoff, or MECO, occurred 2 minutes and 17 seconds after launch. After separating from the second stage, the Falcon 9 first stage then returned to Earth, making a successful touchdown at Cape Canaveral's Landing Zone 1. Meanwhile, the upper stage ignited as scheduled, taking the classified payload into orbit. Little is known about the mission other than the flight path took NROL-76 on a northeasterly course over the Atlantic Ocean. Our only clue are the official warning notices, known as NOTAMs or Notice to Airmen, which were issued for an area corresponding to a launch orbital inclination of about 51 degrees. A second set of warning notices were issued for the Indian Ocean off South Africa for 4.5 hours after the launch, and that implies an upper stage deorbit burn and re-entry about 2.4 orbits after liftoff. When combined, these trajectories point to a LEO or low Earth orbit inclined at around 51 degrees with an apogee of about 375 kilometres and a perigee of about 355 kilometres. And that's an unusual orbit which doesn't match many existing National Reconnaissance Office spy satellite flight paths. Speculation has suggested this could indicate a new fourth-generation quasar constellation satellite placed into a low transfer orbit which could later be manoeuvred into a Molniya orbit. Molniyas are highly elliptical orbits designed to use an extreme apogee of up to 40,000 kilometres to keep a satellite over a specific part of the Earth, usually above the polar regions, for an extended period of time. You see, geostationary satellites are placed over the equator, and so they don't provide good coverage of polar regions because of the curvature of the Earth. That's where the Molniya orbit comes in. Quasar is a code name for the National Reconnaissance Office's STS, or Satellite Data System Communications Relay Satellites. They're used for transmitting real-time data from reconnaissance satellites in polar orbits. On the other hand, it's also been speculated that NROL-76 could simply be a new technology demonstrator spacecraft. Either way, I guess we'll never know, which is exactly what the National Reconnaissance Office want. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important, or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.